the signal path. I'm finally fully set up in my lab and I'm going to do a product review for you guys today. Today we'll talk about the Tektronix MDO4000C series, which is sitting here right behind me. This is the third iteration of the very famous mixed domain oscilloscopes category of products from Tektronix. These instruments give you the ability to do correlated measurements between analog, digital and frequency domain at the same time, all in one instrument. This third iteration of this unit has additional capabilities such as arbitrary function generators, digital multimeter frequency counters built into it, as well as general performance enhancement. Now, one of the things I didn't do when I reviewed the original 4000B series was that I didn't do a teardown, and this time we're going to do a full teardown and analysis of how this instrument is actually architected and how it's built and how it's put together, which should be very, very interesting. This was one of my favorite units in the lab. Its capabilities are quite amazing. It has really a big depth and breadth of functionality that it can do, of a lot of software functions as well as the interface with the signal view, and I'm going to show you all of that. But before you watch this video, you almost have to watch the review of the 4000B, because everything I talked about there in terms of measurement capability still applies here. So you haven't seen that, go and watch that first, and then you can come back to this one, watch the teardown and watch a whole new set of experiments that I've built just to show you some additional capabilities of this unit. So there's a lot of interesting things to talk about. There's going to be over 3 hours of material dedicated to this unit because it can do so much, and I wouldn't even be scratching the surface. So if you like that, go check that out. I put a link in the description so you can find it very easily, and then come back and watch this. So let's get started. And here's the MDO4000C series compared to the MDO4000B series. Naturally, they're going to look quite similar because this is an iteration on this original instrument. Now, from the front panel, a couple of subtle differences. One of the things that I really appreciate is that the old MDO4000B series, these knob adjustments did not have a push button on them, so the horizontal and the vertical alignments could not be zeroed by just pressing on top of the knobs themselves. You'd have to do it through software. But now in this iteration, you can actually push these buttons, which is fantastic because there's so many times that I accidentally kept pressing these and it did nothing, whereas here now we can finally zero and level these quite easily this way. The other couple of minor differences is that the B4 button, which was a 4th bus configuration on the B series, has now been replaced with an AFG button, which is great. AFG is the arbitrary function generator. This unit has an arbitrary function generator that can generate up to 50 megahertz. It has 127,000 sample memory, which you can upload your own waveform into, and has a whole bunch of built-in functions already in there. And at the back of the unit that I will show you in just a moment is where the output of that is taken, because the front is still the same as the old unit. We've got the 4 channels and the RF in the front there. And the triggering is all at the back, as well as the AFG output. And the AFG output can generate its own triggers from the trigger output, from the auxiliary output, and that can be used to synchronize back to the input. So it's quite handy and quite flexible from that point of view. A whole bunch of other differences have been made internally. The performance has been improved, as well as the fact that now you have a DVM, a 4-digit DVM, as well as a 5-digit frequency counter built into the channels. So even if the channel is not being displayed, you're still able to use the DVM functionality. So it really is an all-in-one instrument with the addition of the function generator and the DVM and the frequency counter and all the different protocol decoders and a whole bunch of softwares that are built into it. It really is a single instrument that can do quite significant amount of functions all at once, and I will show some of that during the review. Like I said, it's definitely one of my favorite instruments, so I'm eager to show you what's going on. So let me show you the back of this and then we will take it apart. And here's the back of the MDO4000C. Nothing surprising here. It looks very similar to the old generation with the addition of this AFG arbitrary function generator output, which is fantastic. And if there's time, we will take a look at it as well. The Ethernet VGA port is quite typical, and host and device USB. One of the things I wish they had done on the C series is that I wish they had introduced a USB 3 on this iteration for faster data transfer, especially when you're using it with signal view, but I'm sure that's something that they would do in a future generation. Lots of nice ventilation, everything looks great, base amount compatible, of course, just like the old one was. So it looks pretty good, and no surprises there. Now we should take it apart and see what's inside of it. Well, let's go ahead and take a look and see what's inside the MDO4000C. Now, before I get started, I want to express my gratitude to Tektronix for sending me the raw board from the instrument so that I don't have to open the one that's sitting on my bench. This also shows a degree of openness and transparency to their fans and their customers that they would like you to see what's going on inside their instrument and exactly how it's built and what the architecture is. This is really important, and I really appreciate that, because in order for you to get the best measurement out of any instrument, you need to really understand how it is designed, and its weaknesses and its strengths need to be considered so that you can get the most out of it. And this is basically Tektronix' way of telling you, here, this is how we built this is how it's made, so you can get the best out of it. And MDO is definitely one of my favorite instruments, so I'm really excited to take a look and see what's going on. Now, one of the very first things to note is that this is a multi-board construction. We have 3 separate boards, one over here, and a board that's sitting underneath this one, which we will take a look at. Obviously, the power supply is not here. Just not that interesting to take a look at anyway for our purposes. Now, it is a really beautifully designed board. This is a 3rd revision of this instrument, and I'm sure many revisions of this board has come and gone, and it's flawless. It's wonderfully engineered, it's clean, it's got a great layout design, and obviously works quite well. So let's take a look at what's going on a little bit more in detail. So this board over here, which has got the Ethernet, the VGA, the USBs, and the BNC connectors at the back of the board, is connected to the main motherboard with a PCI Express interface. So we can take this out and we can take a look at it later so that it doesn't block our view. There it is. We'll take a look at this a little bit later. Now, the main board has all of our digital stuff on it, as well as the A to D converters. So basically, the analog portion of this ends at the ADCs, and I'm going to talk about that in full detail in just a little bit. The rest of it is quite straightforward. We have obviously our power supply section, as you can clearly see, with an interesting heatsink design here. This is where the main power comes into the unit, and we're not going to talk too much about that. Now, what is underneath this heatsink here, and I'm not going to remove the heatsink because this is just an application processor. This is where the main firmware and the operating system, which is an embedded operating system of this entire instrument, runs. So we're not going to take a look at that. It's going to be a generic application processor of some type. It's got some memory surrounding it and so on, and also its proximity to the PCI Express interface confirms that it's handling those traffics and the data coming in and out, driving the VGA and all that stuff is handled through that portion of the circuit. So nothing that interesting over here aside from that. Now, this portion is where the interesting stuff begins. Let's start from here. We have a 100 megahertz crystal. This is a high precision, high stability crystal, which is a main clock for the entire instrument, for all the ADCs and everything else that's there. That's quite critical. The performance of the ADC is obviously going to depend on the quality of that and the quality of the PLL that's locked to that. Over here, we have an FPGA. In fact, we can take this heatsink off, and this is an Altera FPGA, and this Altera FPGA handles a whole bunch of traffic coming from this portion of the circuit, and I'll talk about what's going on over there. So all the digital this is more of a glue logic. It's not actually interfacing with the A to D converters directly, but it handles the traffic from various ICs, talks to the main application processor, talks to the ADC demuxes and the SerDes over here, and it also talks to this chip, which is a Tektronix MDO4000C. And this is a Tektronix branded and probably Tektronix designed trigger IC, and it handles all the triggering of multiple channels of the A to D converters coming from the analog inputs, as well as the spectrum analyzer input, and also interfaces to this portion of the circuit. And on the other side of this, there's a connector which then goes to the digital inputs, because remember, this is a mixed domain. It has analog, digital, and RF, and this is one of the other things that this chip seems to be handling. You can see the traces of it going to the protection circuits and the buffers that come from the digital input. So the architecture on this side is pretty clear, at least up to here, and we know exactly what everything does. Now, starting to this side is where things begin to become very interesting. Now, we may be tempted to think that because this instrument has two A to D converters, that one of these is dedicated to sample 2 analog channels and the other one dedicated to sample the other 2 analog inputs, because this is a 4-channel scope. But in reality, that's not what's going on here. Because we have an RF spectrum analyzer input, one of the A to Ds is dedicated just for that purpose, and is using all of its resources for doing an IQ down conversion directly from the RF input, and I'll talk about that exactly what's going on in a bit of detail once we look at the RF board. But let's look at this one here. So this means that this ADC will have to be able to have 4 analog input channels and process the data from the 4 channels of the oscilloscope. And in fact, that's exactly what's going on. Now, if I were to remove the heat sinks from here, we will see that both of these ASICs are branded Tektronix. and therefore there's no information available about them. But we can decipher about what's going on by thinking about the architecture of this overall system. So this is an HDF204, a Tektronix ASIC. This is an 8-bit 12 gigasample per second A to D converter, but in this instrument is not being run at 12 gigasample per second. They're running it at 10 gigasample per second. Now, interestingly, this ASIC also has an input bandwidth which far exceeds its Nyquist criteria. And this is one of the reasons why they're able to do what they do with the RF input, as I'll talk about that a little bit later as well. So this has about an ENOB of about 7 bits, 6 to 7 bits, and it requires a quarter rate clock. And that again also makes sense because it means that a 4-input A to D converter running at a quarter rate can be used to sample 4 analog channels. And in fact, if you turn all 4 analog channels on this instrument, the sampling rate drops from 5 gigasample per second to 2.5 gigasample per second, because all of the 4 time interleaved ADCs inside this ASIC are now going to be used 1 per channel. If you turn 2 of them off, then 2 of the time interleaved sub-ADCs will be combined into a 5 gigasample per second, and then you're going to have 5 gigasample per second sampling at a 1 gigahertz bandwidth. So this all makes sense and is consistent. Now the output of the A to D converters are 32 channels coming from the SerDes running at 3.125 gigasample per second, gigabits per second, I'm sorry, and that 3.125 gigabits per second has to be demuxed, and it requires 2 ASICs just to do that. And one of them is going to be handling 16 and the other one is going to be handling 16, and these themselves are 1 to 4 demuxes, which means the output of these ASICs is going to be 128 channels coming out in LVDS format. And also it's pretty interesting that these ASICs do more than just demultiplexing. They actually interface with the memory that's directly on this board, and there's a whole bunch of other memory on the other side. And this is the memory of the, the main memory of the oscilloscope, and also the memory that is used for the RF input. Now, this also should be doing more than just that. Aside from the memory and the demuxing, probably does some ASIC computation directly on the RF data coming in, to be able to reconstruct the signal based on the architecture of this, because this is doing some IQ sampling, some fancy reconstruction of the data, at least based on my understanding of looking at it, and it requires some ASIC to do that. I mean, you could do it in software, but I would imagine that'd be way too slow in that case. Now up here, there are 4 holes, and these 4 holes are where the heat sinks are sticking through for the RF board at the back. But now we understand everything that's over here and the overall economy of this board in terms of how the resources of A to D conversion, FPGA, demultiplexers, memory, application processor, and everything is connected to each other to make the whole thing work. So we have a rough idea of the architecture. Now in the middle over here, we have an analog devices IC, which is the clock generation. It has multiple outputs, and that also makes sense because you're going to need multiple outputs to drive the various ADCs. And this is rated at 2.5 gigahertz, which also makes sense because these are quarter rate ADCs, which means the maximum frequency they're going to be running is 10 gigasample per second. So that's also consistent. Everything so far makes sense, and everything seems to be working together. Now I'm going to disconnect this and separate them from each other because they have some SAMTIC connectors which connect these 2 boards together. Here we go, and we can take a look on the other side very briefly and see what's going on this side. Here are the holes where the heat sinks were sticking through, and here's the rest of the memory that I was talking about. The back of it is pretty bare and there's not much there. You can see the BGA footprint of all the ASICs that are there. Here where the 2 A to D converters are, here are where the demultiplexers are, and the main FPGA and main application processor there. This is the connector for the digital inputs, and everything makes perfect sense. Some flash memory. Now if I go back over here, there are other indications on, let me take that out of the way, and we're going to take a look at that separately. If I turn this around so you can see it from this angle as well, you can clearly see over here the traces that reveal that the A to D converter here is used for the 4 channels, because if you look at these traces over here, they're all 4 traces coming from the 4 A to D, the 4 analog channels coming here, and they're all distributed and sent to this one. And in fact, if you look over here where the analog devices clock generation is, one of its output is going through additional filtering here, and I'll see filter bank over here before it's sent to the A to D converter. And I wonder they need to do that in order to really clean it up, to make sure that the signal reconstruction from the A to D converter is successful, because if you don't have a very good clock over here, because you're trying to reconstruct signals from two different A to D converters, it would be a mess. And I believe this is what they're doing. Based on, again, my observations over here. There is no data sheet, there's no schematic, so this is all kind of reversed engineered. But it looks pretty nice and very, very sophisticated design here, especially once we take a look at the RF section, so you can appreciate the complexity of the engineering that's gone into it. But we now understand at least what's going on this board. So let's move on to the other board over here and see what's going on. Now, I've already taken the shield off this. In fact, I don't quite remember where I put it, but this is the main RF board, and it looks absolutely amazing. There's a lot of really neat stuff on this board. So the board was protected by this, and we've seen things like this all the time, and I've shown it in many different videos for different RF equipment that I've taken apart, and each individual compartment very well shielded from each other, as to be expected. And this sits directly over here, and I've already taken it apart. This is custom machine and everything, and this is very important, particularly for this, because of its, I mean, as with any spectrum analyzer, harmonics, unwanted spurs, unwanted signals, coupling between traces where you don't want coupling can totally ruin your spurious-free dynamic range of your spectrum analyzer. And this is one of the things that they had difficulty with this instrument before, because of the frequency planning, and one of the major improvements on this version of the instrument. So let's go ahead and take a closer look over here. Let me zoom in here so you can see how beautiful this thing actually is. So we have 4 analog inputs here. On the other side, we have all of our BNC, so channel 1, 2, 3, and 4, and our RF input. On this side, there is really not much there, so there's no point to look at it. But it's interesting to see that the connectors are directly attached to the main board here. And the reason is, once you do this, you don't have to worry about calibration and variability and so on. Once this is there, you can do everything here and ensure that it wouldn't change after assembly, which is quite handy, and a lot of manufacturers are doing that. Now, underneath these cages over here are obviously going to be every thing required for front-end handling of the signal, the attenuators, the preamp, the detectors, the protection circuitry, everything is there. So I'm not going to take one of these cans off simply because they're soldered on. There's really not much there that is unexpected. This basic analog input handling of the oscilloscope, 1 gigahertz bandwidth, fairly well established. This is a very low noise instrument, so they have obviously done some good engineering with a good front-end amplifiers and so on. But the main amplification and the main ASIC that handles the signal conditioning for the A to D converters, actually, which one of these did I take off? There we go, this one, is actually handled by this ASIC over here. This is an HDF144C. There is no information available about it, but it's obviously a Tektronix branded ASIC, and it handles the data coming from the analog channels. 1 per analog channel is a high frequency amplifier. Lots of gain, lots of bandwidth, calibrated, good phase response in order to make sure that the signal is well conditioned for the A to D converter. The front-end noise and the performance of the instrument is going to be determined by this. And in fact, if you remember when I did a teardown of the S-series oscilloscope from Keysight, they too had done a custom ASIC just for that purpose in order to be able to get the noise as good as they can. So seeing so many customized ASICs by Tech for various applications to optimize the performance of this is very promising. Means that you're going to get the best out of this. There's very little off-the-shelf components on the critical signal paths, no pun intended, which handle the major linearity and the noise requirements of the instrument. So let's take a look at the RF board where all the magic happens. So we're going to follow the signal path and figure out how this instrument actually works from the RF point of view. Now, the very first thing the signal meets right after the type N connector is a decoupling cap. Now, that decoupling cap right over here is to be expected because this instrument is AC coupled at the input and the lowest frequency of operation is 9 kilohertz. Right after the decoupling cap, we see a mechanical relay, and a mechanical relay is also to be expected because you wouldn't want to put a solid state relay in the front, because solid state relays have linearity limitations as well as the fact that a high power condition can actually damage them. A non-solid state relay like a mechanical one like this has essentially infinite linearity, and they use this to either create a through path or a 20 dB attenuated path in order to protect the instrument and also to provide the proper level that you need at the input to the rest of the circuit. After that, you have a long trace, and this trace is now going to meet its first solid state switch, and that can select either from the input or this other circuit that's over here. Now this other circuit has a high-speed diode right here and an amplifier that follows right after. This high-speed diode can give you broadband noise. It's in fact a noise generator. So you can select either from a spectrally known broadband noise source or the input signal. Now a noise source has many benefits because it's white and because it's statistically evenly distributed. You can use it for calibration. You can use it for getting even more spurious-free dynamic range from the A to D converter by scrambling your signals in some ways. There are a whole bunch of tricks you can play, but this is likely used for calibration and to just provide a flat response, to just figure out what the ADC is doing, perhaps to during some calibration or so during some signal path compensation techniques they are using this. I've talked about dithering and noise injection and stuff in some of the other teardowns that I've done, but it's interesting to see one of those circuits here. Now after that, we see some sections of the circuit which are very repetitive and periodic, and that's because they're essentially identical. We have 1, 2, 3 electronic attenuator sections where you choose either between a through path or a path that has an attenuation built into it. And by having different values of attenuation, you can then have a really fine hardware attenuator, selecting between every 2.5 dB or 5 dB steps and so. And this is exactly what these couple of attenuators are doing in a row. And then after all the electronic attenuations and everything, finally here, we meet our first amplifier that can amplify the RF signal that you're putting into the circuit. You either select between a through path or a path that has the amplification. So if the signal is really small, this is how you can recover some of the dynamic range and reduce the noise figure of the front end by having this amplifier over here. And this little inductor that you see here is the bias inductance for that particular amplifier. And then you have again another solid state switch to select between the two, and then you meet another switch yet again, and this is where your bands are separated. Remember that this instrument actually has 3 internal bands, and those bands go from 9 kilohertz to 3.75 gigahertz. They go from 2.75 gigahertz and 4.5 gigahertz, and finally 3.5 to 6 gigahertz. So this is the reason why there is 3 distinct paths here. So the signals below 3.75 gigahertz follow this path, and those signals are the ones that are directly sampled by the ADC. They don't need to be down converted anymore. The other 2 paths have the down conversion. So let's go ahead and follow this one first. If I go all the way over here, there is some switch again here which is back terminated to 50 ohms. This is for signals feeding back and so on. And then you go over here, where you meet your other 2 signals over there after they've been down converted, and then finally going forward. And then let's follow this a little bit further. We have an amplifier here, and then over here as the signal continues on, we tap off a tiny portion of the circuit, amplified once again, amplified yet again, and then finally putting it through a logarithmic detector. This is a 70 dB dynamic range logarithmic detector, and this is used for triggering on the RF power, perhaps for ADC ranging, for overload detections, and a whole bunch of other functionality. This can be used for those. Logarithmic detectors are used in receivers all the time, and this is no exception for the purposes. So this is the main input signal path that is not down converted, simply follows this path over here and then reaches over here. Now let's go on the other side. Now what happens to the other 2 bands? Well, after we split here, we split again. We either choose the low band or the high band, and then both of them join back again. These are nothing more than filters, and there are hybrid components actually that have been added to it later on. And I've talked about these type of filters many times before. These are interdigitated fingers, and they're very, very common. And this is on a different substrate so that you can have even higher quality factor than you would normally have on this material that they make in the original PCB from. And then they go forward there again, some more back terminated 50 ohm switches, and after some more filtering, we meet our first mixer. And this mixer then down converts the signal to match the same band as the original sub 3.75 gigahertz band. Remember that these paths all overlap sufficiently so that the instrument has always at the minimum a 1 gigahertz instantaneous bandwidth. So how does this mixer stuff work here? Well, they've done some clever stuff here. So they have 2 VCOs, and these VCOs run from a 9.6 gigahertz to 10.8 gigahertz, and the other one from 12.44 to 13.76 gigahertz. Now they're not using the fundamental output. That wouldn't make sense. They're actually using the half rate output, because these 2 VCOs also provide an F/2 output, and that would be 4.8 to 5.4 gig and 6.2 to 6.8 gig. So both of these VCOs are needed depending on which band is selected, likely depending on which of these paths is selected, and you need to down convert using the frequency output from those. Now they've done something interesting here. They take the two outputs of the VCOs and they feed them to the two inputs of a Wilkinson divider. And then they take the output of the Wilkinson, this is actually more of a Wilkinson summer in this case. The Wilkinson power combiner then goes into a Wilkinson power splitter, and then they take the output from one and they put it into a PLL core, and they take the other side of the Wilkinson and then they put it through an amplifier and then back into a mixer. So this is a clever way of selecting between the VCOs and at the same time feeding the PLL and closing the loop, simultaneously splitting the signal and passing it to the mixer. So it's a nice little circuit there, and this is how they close the loop with the VCOs. And depending on the frequency selection and so on, then you get the right band and you get some amplification again, some filtering again, and the signal joins back. So pretty interesting and very straightforward architecture over here, and this is very common. These techniques are widely used in the industry, and it all comes to planning your frequencies properly, choosing the right components, figuring out what the minimum number of filters you need so that you don't blow up with a whole bunch of loss and a whole bunch of expensive equipment components there. So it's pretty straightforward. And then you reach this component here, which is a coaxial balun going from single ended to differential. And this is likely required so that you can provide a differential signal to the ADCs, because the ADCs are surely differential. And then you have two amplifiers here that amplify each of the outputs of the differential signal. It's a little bit unusual to see that they convert to differential and then they don't use a differential amplifier. So it makes me doubt a little bit about what's going on here, but it seems to me that that's what they're doing, that they're individually amplifying each of them. Now on the other side of this is where some additional really interesting stuff happens. Over here is the VCO, 4.5 to 5.5 gigahertz or so, and that VCO is amplified and filtered, and then it's split into two, and one path goes over here with the reference 0 phase, and the other one goes through a quadrature transformer, giving it a 90-degree phase shift. So now you have a 0 degree and a 90-degree phase shifted signal of the 5 gigahertz VCO, and it seems like it joins the input, which is really interesting. Now, let's remind ourselves that the spectral content of the signal here is from 9 kilohertz to 3.75 gigahertz. The ADCs that I showed you on the other board have a maximum sample rate of 5 gigahertz each, and there are two of them on the die, which means that the Nyquist criteria means that they cannot sample more than 2.5 gigahertz without aliasing. But if you have two of them, you could actually subsample the signal and then using digital techniques recombine them and reconstruct your 3.75 gigahertz spectrum. And that's what I believe is going on over here, and this is why they're sending this to both of the ADCs at the same time. Now what I suspect they're doing here is that they're using this perhaps as a calibration in order to align the ADCs with the correct phases, because if you were to sample a 5 gigahertz signal with a 5 gigahertz sample second ADC, you're going to get a DC, and that DC can then be used to align them, which kind of my guess here that this IQ transformation here is used for alignment, and which you could think of it in terms of IQ down conversion also. You can think of the ADCs as mixers and think of them as IQ down conversion, but I prefer to think of them in terms of what happens to the spectrum individually. This is kind of my guess about what's going on over here, but if perhaps one of the Tektronix engineers wants to chime in, I'd love to know exactly what's going on, but this is kind of my hypothesis. So otherwise, other than that, it looks pretty straightforward, and I think it's a really nice design. And the techniques they've used here for signal distribution and the way they've architected it in such a small area is great. And you can see the expertise there. This is the third time they're building this, so they really know what they're doing. And there was one other thing that I wanted to very quickly show you. And I apologize for the noise because it's still sitting in the anti-static bag. I put it back in the bag. And it was this last piece here. The piece that provides the arbitrary function generator output, the auxiliary output, the trigger, and all that. Now over here is pretty straightforward, nothing fancy going on. Obviously the RTC clock is here and so on, but what's underneath this heatsink, I suspect, is the DDS, because the arbitrary waveform generator of this instrument uses direct digital synthesis, and I believe that's what's under here. And therefore then you can see from a proximity to the AFG output, and they can then download data into it and so on, and the data has to come through the PCI Express. That's what I believe is there. I don't want to take the heatsink off because it's really stuck on, but that kind of makes sense. And you have a switch here that perhaps this switch in fact I believe enables or disables the output. So really nice. pretty happy with it. I think very good design. So now that we've seen what's inside it and we kind of have an idea of how it works, we should be able to perform some really cool experiments with it. So before I show you the experiment that I prepared for this video, let's just remind ourselves of the experiment that I had built before when I was reviewing the MDO4000B series. Now I'm showing this here again because I want to remind you, as I said in the beginning of the video, that everything I did in the original review is still perfectly valid for this iteration of the instrument as well. Except that in this iteration we're going to also focus on some of the improvements and advancements and additional functionalities the MDO4000C has gained. But also I don't want to repeat myself, so I have designed a completely different experiment for this instrument. Now, the old experiment had an IQ modulator with a diversity antenna switch at its output and a whole bunch of various problems from its DC biasing, from digital corrupting the RF signal, the diversity switch not working properly, and we were trying to track this complex mixed domain setup using the MDO, which is in fact what it's designed for. And I wrote those problems down and we went through them and we solved all of them and traced them all out, and using only just the MDO by itself managed to detect and clear all those issues. Now for the MDO4000C series I have prepared this experiment, and this experiment is quite different from the other one because this is talking about a transmitter where it employs RF encryption directly built onto the carrier frequency, and this is a frequency hopping style of encryption. What this means is that there is going to be a frequency hopping DSP somewhere which is going to control the carrier frequency of our transmitter, but the algorithm it uses to choose the carrier frequency between various packets that are being transmitted is a secret. That sequence, is encryption sequence, is a secret so that other people listening to your transmitter won't be able to predict what the next carrier frequency is. And this is a technique that's used in various places. And it's difficult to meet FCC regulations with something like this. So usually, for example, military likes to use this type of applications. But this type of frequency hopping is present. In fact, Wi-Fi uses a type of frequency hopping like this one. So having said that, let's go ahead and follow this and figure out what we are first of all testing, and then we can look at what kind of problems it has. So the frequency hopping DSP sets the frequency of the Silicon Labs PLL. Now this Silicon Labs PLL has multiple outputs, we're only using one of them. And what this does is that it takes a 25 megahertz crystal and is able to multiply it to a really wide range of output frequencies. And it's controlled through an I2C interface. So we have a digital interface over here, and it will set the carrier frequency. The output of this Silicon Lab module then goes into a low-pass filter to clean it up, to make a nice sinusoidal signal, and the frequency then coming out can range anywhere from 85 megahertz to 125 megahertz. The exact frequency is going to depend on the frequency hopping algorithm. The output of that is then fed into a regular double sideband mixer, and that mixer is fed with an LO coming from a voltage controlled oscillator, and that voltage controlled oscillator is going to need its own PLL, it's going to need its own VCO control. This itself can be a mixed domain problem. So we have a VCO control circuitry here which then sets the carrier frequency of this VCO at about 3.6 gigahertz. And this 3.6 gigahertz is a fixed frequency. It's going to mix with this, which is a hopping frequency, and it's going to give you a scrambled LO. And that's the foundation for doing your encryption. Now this scrambled LO then goes into an LO leveling amplifier. I put a picture of it over here. This is an HP part. So the scrambled LO goes in here and it gets amplified, and this amplifier has a detector, and that detector is an analog voltage proportional to the strength of the signal coming in, and that's going to be used for leveling the LO in order to ensure that the transmitter is working properly. And this itself again can be a mixed domain signal because you have an analog signal which then can go into a digital loop, come back and adjust the gain of the amplifiers, a whole bunch of complexity going into that. And then the LO signal finally is fed into an IQ mixer, and this IQ mixer gets its IF, I and Q signals from an N6050A, which is the same baseband IQ generator that I showed in the previous video. It's a very nice, extremely linear, very high dynamic range system over here. So then the output of that finally after the mixer becomes our RF carrier, and that RF carrier now has our modulation, our low frequency hopping algorithm, everything is on there. So this system, as you can see, clearly has digital circuitry in it, analog circuitry in it, it has RF circuitry in it, it has a whole bunch of different types of signals present at the same time. So if you want to find problems in a system like this, you typically need multiple instruments because you need to look at all these signals at the same time. But correlating them is of course the most difficult part, and that's where the magic of the MDO comes in, because we are able to do all these correlated measurements all in one instrument. So again, I'm going to take the R digital, analog, and RF signals and feed it to all the various ports of the MDO4000C, and we're going to be able to take a look at that. And the people who've built this prototype that have given you, for example, this task to figure out what's wrong with this, they have written down the list of the problems. So apparently this particular prototype has intermittent packet loss and link loss problems, which is a really difficult thing to solve. It has a very high BER floor, so its error rate is very high, and this happens at all carrier frequencies. So there's something fundamentally wrong with the way the carrier is generated. And they also want to know if the LO leveling amplifier, which is basically this amplifier, they want to make sure that this amplifier has sufficient bandwidth, and we want to be able to measure the detection bandwidth of this, which, as we will see, is not that easy to do. And finally, there is frequency hopping timing problems, which again is quite difficult to solve, so we have to find out where this is coming from. And if we solve all of these problems, then they want a final EVM performance and for our records, so that we can say that, okay, the system is fixed. And we want to do all of this within this Tektronix MDO and within the Tektronix Signal View software. And this is quite a bit of work, as if you've ever worked in these type of systems, you would know that these are not easy problems to detect. So now that we have the block diagram or prototype, let's go to the bench and look at this prototype and correlate the components to this, and then we can actually go ahead and do some measurements. And here is our test setup. I have shown the block diagram I just talked about here on the iPad for comparison, so we can go through it fairly quickly. I have the frequency hopping DSP algorithms implemented on an Atmel processor. That processor then controls the Silicon Labs module, which then generates the 85 to 125 megahertz hopping frequencies. After that, we have our low-pass filter, which is this blue module over here. We have an AC decoupling cap there, and then going into our first mixer, which is right over there. The VCO comes from this particular module, which is also an HP VCO, and is controlled by some power supply. I'll show you that in just a second. The output of that mixer, which is now the scrambled signal, goes through our HP amplifier, just like shown here on the block diagram. The output of the HP amplifier, the detector output over here, is taken out from this cable right here. We'll be looking at that using the instrument. And the output of the LO, which is now fully amplified and scrambled, is then fed into this IQ modulator, and these are the I and Q inputs of the modulator coming into the system. Now, as you can see from this is truly a mixed domain setup, because we have digital, analog, and RF all together, and detecting problems in something like this is very difficult. But because we have the MDO in one place, we're going to look at the signals in various locations. So here is our MDO sitting right there, and you can see I've connected some of the cables to it already. We have the digital stuff and some of the analog stuff, and the RF is still not connected. The power supply that powers the VCO is going to be this Rigol DP1308, which provides a plus and minus power supply. And to power the amplifier over here, this amplifier right there, I'm using a Keithley 2280S power supply, which is a high precision power supply, which by the way is a really, really nice unit, and I quite enjoy using them in the lab. The IQ inputs come all the way from across the lab where the black keyboard is, and right behind it is my PXI module, where it has the IQ generator PXI module in there. So we'll take a look at that later a little bit closer when I'm trying to generate the modulation. But before we even start doing modulation experiments, we have to figure out what's going on with the frequency hopping first, because it's going to be too complex to look at a modulated signal while all these problems exist. The output, the final output of the system is over here, currently unconnected. So I'm going to break the system from here, and I'm going to look at this signal directly and take that into the MDO, and that will allow us to look at our frequency hopping as a first step. So let's go ahead, turn on the instrument, power this whole thing up, and start doing some testing. It should be pretty interesting to see how this can be done. Alright, power supplies have been turned on. I think you should be able to read that as 13.5 volts, 78 milliamps from here, and plus or minus 12 volts, 34 milliamps, and that powers both our amplifier as well as our VCO. And the Atmel processor can be powered directly through the USB port, and that's what I'm going to do. I'm going to power that through the USB port. Now the instrument is all booted, ready to go, and now we can begin our experiment. Alright, now the instrument is up and running. I have connected our LO hopping frequency directly to the RF input of the instrument, and we can go ahead and see what that signal looks like. Now, because of the angle of the camera, you're going to see the reflections of my hand on the screen. The screen is actually not that reflective, but the camera picks it up because of the angle it's pointing at. I'm going to try and keep my hand out of the way. So let's go ahead and turn off channel 1 because there's nothing even connected to it. And we can go ahead and enable the RF channel. And as soon as I enable the RF channel, you will see that, well, first of all, we're going to see a sweeping frequency, which is to be expected, but then we also see an error saying that the signal is clipping and a possible distortion present. Now remember, the architecture of this instrument is such that we are doing an FFT-based spectrum analyzer with a really large capture bandwidth using the ADCs. And because it has such a huge instantaneous bandwidth, and at the minimum it has 1 gigahertz, and it can have all the way up to 3.75 gigahertz of instantaneous bandwidth, even if there's a signal present outside of the region you're looking at on the screen, you can still cause distortion. But the instrument is smart enough to be able to tell you that the signal is present, you should change your reference level and have additional attenuation, and that's easy to fix. We can go ahead under amplitude and change the reference level. We can make the reference level, let's say 15 dB, and that switches in a front-end attenuator, and the problem is solved. Perfect. Now the center frequency here is 1.5 gigahertz. That's not what our carrier is. We know our carrier is sitting at 3.66 gigahertz. We can go ahead on the frequency and change the center frequency to 3.66 gigahertz. There we go. That's good. We begin to see some signals, and you can see that the peak of the signal is as large as 10.7 dBm, and therefore that makes sense why the signal was clipping before. But this is looking at a huge span. Our signal is not occupying that much span. So we can go ahead and change the span to 80 megahertz, which is the span of our signal of interest. And there is our signal, and it's hopping around as to be expected. It looks very randomly hopping, again because it's encryption, and some encryption key determines the hopping pattern, so we don't have to worry about that. But the signal doesn't look very clean, and like this you don't know if there is any problem. You don't know if the frequency hopping is successful. Is it random? Is the signal always there? All of these are questions which you cannot answer very easily on a traditional spectrum analyzer. If you have a real-time spectrum analyzer, then you would be able to capture some of the intermittent effects. But this can do much more because it has all the analog and digital inputs. So let's go ahead and check to see if frequency hopping is even working, and use one of the features of the instrument which allows you to plot RF activities as a function of time. And that's really, really handy, as we will see. So we're going to enable that particular function. If you press the RF, you're going to get all these various options down here, and we have RF versus time traces. Now under RF versus time traces, we can either do amplitude, frequency, phase, and a few other options versus time. Now we know this is frequency hopping, so I want to look at frequency versus time. I'm going to turn on frequency versus time, and as soon as I do that, I begin to get some frequency hopping at the very top. Now, this is one of the very first little tiny bugs that I discovered. The first time you turn this on, for some reason this portion of the graph doesn't always get updated. Sometimes it gets updated, sometimes it doesn't get updated. And it's a tiny little bug in there that they have to fix in the way the data is displayed. But we can change our scale, and as soon as you change your scale, the problem is solved. And even if you go back, the problem is gone. So right now we're looking at the frequency hopping, but we're looking at a 4 microsecond window. Now 4 microsecond window is too short. The frequency hopping here is happening at a slower rate. So we have to zoom further back out and look at a much larger duration of the signal. So let's go all the way out, 10 microseconds, 20, 40, 100, and 1 millisecond. Now at 1 millisecond, the instrument has to do a lot of computation. And 1 millisecond for an ADC is running at 10 gigasample per second, capturing the signal, doing the digital down conversion and reconstruction is a lifetime. So at this point, the instrument becomes a little bit slower because it has to capture all this data and process it. So right now we can see here, this is our frequency, this vertical axis is frequency, and this horizontal axis is time. So you can see as a function of time, we're doing frequency hopping, exactly what we would want to do. And it's changing randomly with some encryption key. And you can see that it's not really, doesn't have any periodicity that you can detect very easily, and that's to be expected because the key is longer. But every once in a while, we have a chunk of data here that all of a sudden goes crazy. We have all this noisy frequency content, and we don't know why. Well, I want to figure out what's going on there. What exactly is happening during this portion? Now remember, the instrument is taking the peak of the RF signal and then corresponding it to one of the amplitudes over there. So if I do a single capture, I should be able to analyze the signal a little bit more carefully. Now note that this is random. It happens at a different location each time, and therefore making it very, very difficult to capture normally. You see, right now there's actually two very close to each other. So it's completely random, and there's one here at the very end. So let's do a single capture. Now I haven't defined any trigger, so it's waiting for a trigger. I'm going to do a force trigger. I'm going to force a trigger and it's going to compute and it's going to show up on the screen. There it is. So right at the end over here is one of the parts where the signal is not working. Now I'm going to press the search and this opens a zoomed view of this RF frequency versus time, and the instrument will compute the RF spectrum for the duration that I choose to look at. Now this is where the trick is. This is where you need to really understand how to use the instrument to get the most out of it. Right now it's very small and hard to see, so let me zoom in a little bit more. If I zoom in a little bit more, you can see that yellow or orange bar at the bottom growing and shrinking. The length of this in time is the duration in which the instrument computes this spectrum. Now I can move this around and look at it at anywhere during this capture window and see the corresponding spectrum for that duration. This is what time correlated measurement is all about. And you can do that versus any of the inputs, and that's where the strength is. So let's go ahead and sweep around a little bit and see what we see. So right now we have a carrier of 3.652 at this point. I can go a little bit to the left, and you can see that the carrier here changes. And if I bring my computation to that point, you can see that the carrier moves. If I continue all the way, let's go all the way close to where the failure is. So right now the frequency is here, and in fact I can look at the transition of the frequency and see how the spectrum transitions from one point to another. If I go ahead, and you can see it will compute that right there, compute again. Right now I'm at the very edge, right now I'm in the middle, so I see both of them, because this is where for some time the frequency was here, for some time the frequency is over there, so the computed spectrum will show you both of those frequency points at the same time, which is amazing. This is awesome to look at. Now we can go to the left, and now the frequency has settled to the other channel. And if I continue, is where I'm going to get eventually to the failure, and we can see what exactly is going on once we enter the failure. Check it out. We go into the failure, and it disappears. So now it makes sense why we're getting this thick frequency versus time, because we're in the noise and the instrument just places the peak at the highest value we can find, and that's going to jump all over the place, and that's why you're getting this noisy loop. So basically there is no signal. So during those parts of the activity, the signal has completely disappeared. So we've already found one of our failure modes is that there is an intermittent disappearing of the LO signal. And of course, if there is no LO, nothing else would work anyway. But we can find out exactly what's going on using this time correlated measurement. So right here we have our carrier. Right after, during this transition, you can see it begins to disappear and then it's gone. And if I disable that, you can see the entire range of the activity once again. So what could be causing this? Well, we know that the frequency hopping is handled through the I2C interface, so why don't we look at the I2C signals and time correlate it to this failure? And that's really easy to do because the instrument has digital inputs. I've already connected the digital inputs to the I2C, so we can go ahead and enable that and take a look and see what's going on. Now temporarily, let me turn this off and go ahead and enable the digital signal and put this into run mode. And you can already see some digital activity up there. Let me zoom into the signal a little bit more so you can see a bit better the I2C activities. There it is. There's our various I2C. Let me make that larger so we can take a look at it. We're looking at channel D0. Let me also enable channel D1. We can go ahead over here. We can select the channel D1. And we're going to turn on channel D1 as well. So now we have both of our channels there. Now if you look very carefully, you can see that the channel D0 is the clock of the I2C and channel D1 is the data of the I2C. But of course, as with any modern oscilloscope, we have decoding capabilities built into the scope. All of the decoding capabilities of this scope are enabled, which are options which you can purchase. Let's go ahead and enable one of those buses. So we're going to turn on bus here, and we're going to define what kind of bus this is. Right now it's set to parallel, which is not what we want. We're going to select that, and we can see we have a whole bunch of decoding capabilities, I2C, SPI, and so on. Let's go ahead and choose I2C, which is what I want to do. And there's I2C. And we can define our inputs so that it can do proper decoding. As soon as I click on that, I have the option of choosing what is clock and what is data. Right now the clock is set to channel 1. That's obviously not correct. Our clock is channel D0. We're going to select that, and our data is channel D1, and we're going to select that as well. And there it is. I'm going to move the bus down so we can easily see it, putting it at, let's say, 2 divisions down. I'm sitting at a very awkward angle trying to do all this. There it is, 2 divisions down. So you can see occasionally some bus decoding appears. Now I can zoom out a little bit more. And here's all the various activities that are going on, all the commands sent to the Silicon Labs IC to set the center frequency, and that's generated by our DSP frequency hopping algorithm. And if I go under the bus menu, and if I look at the event table, and turn the event table on, I can see all the different I2C commands which appear within the window that I'm looking at. So I should be able to look at various events and trace them, and I already see that there is missing acknowledgements from the unit itself. So these are software bugs, for example, that you would have to fix. Now that we have this set up, we can go back to the RF. Actually, before I do that, let me also set up the trigger. Let's go under the menu, and let's set up trigger to be channel D0, which is a digital trigger. And this will allow us to have a trigger every time a new I2C command is issued. So now we can go ahead and enable back again the RF versus time trace we had before. Now we have our digital data, our RF versus time data, and our decoded I2C, as well as our spectrum under the same display. There is no other instrument, to the best of my knowledge, that can do this at the same time to the level that this instrument can. So let's go ahead and zoom out again to a 1 millisecond stepping, and we should be able to see our failures repeat again. Now, again, as I mentioned before, when it's in 1 millisecond duration, the instrument slows down. Just think about how much stuff is happening at the same time, so naturally it's going to be slower. I do have to say that I wish it was a little bit faster, and it would benefit from having faster processing. So we can see our failure again. That happens at a different time each time. You can see that next time there's 2 failures here in a row, and if we wait long enough we will see again, and here's another 2, one there at different times again. So now I can do a single capture, wait for the trigger, displays the digital, displays the decoded signal, goes through the spectrum, and there it is. And now I can go back and do what I was doing before and find out what is happening that causes the signal to disappear. Let's go ahead and zoom in again. I'm going to zoom in a little bit more. I'm going to go, I'm all the way on that side. It's one of the other things I wish this thing had. I wish there was a way to center yourself, center the search with a push of a button, like you would do when you press a button on a vertical to center your vertical axis, or when you press this to center, because this doesn't do that. I wish this was pressable as well, so that you could just center yourself again. You don't have to keep going back and forth. So if I go all the way until I catch the failure, where are you? There we go, there it is. So right here we have our carrier, and it seems like there's a command sent to the Silicon Labs IC to the address 61, a data of 17, and as soon as that is sent, for some reason, the signal just disappears. And it goes away. And if I continue going through the failure, and there's a whole period of time where there is absolutely no I2C activity. If I look at the bus, and if I go under the event table, I see that all the events that are in the entire duration listed here, and I can go and trace the one that causes this failure and record that and find out what that command does. But it turns out as I continue on, it moved me all the way to the right again. There we go. If I go over here, after some time of no activity, after a whole bunch of time of no activity, I'm going to begin, I get another command, 60 with the data of 10, and all of a sudden the signal comes back. Now we're back again, and we have a carrier. So what I just did is that I just found out what commands were being sent to the Silicon Labs IC, at what time, and what duration it took for the signal to come back. I have all of that information. This correlation now tells me to go at the correct place in the code, find out what that command does, and see if I can fix it. So I dug into the datasheet and I found out what's going on. By some mistake, during the computation of the frequency hopping, the person who wrote the code accidentally computes the wrong address and the wrong value to write and disables the output driver of the Silicon Labs IC by mistake. So after that command, the output is disabled and the system is hung and is waiting, and since nothing is happening, it issues the next command and it brings the IC back out, enables the output again, and the signal recovers. But that code, because the frequency hopping itself has some random element to it, that erroneous command sent to the Silicon Labs IC is also random, making it very difficult to find. So normally this would have been an absolute nightmare to catch, but because we were able to do the time correlation between the digital and the RF, we can go ahead and figure out how to where that problem is, so we can figure out in the code, look at the event table, find the appropriate, find the command before it, find the command after it, which is very hard to do normally, and then find out what is going on so we can fix the problem. So now that I know I've done this, I can go back to the code and correct the code and see if this problem actually goes away. Well, by tracing the packets and correlating them with the missing LO tones, I managed to solve the problem in the code. Now, if you look at the spectrum, there is no portion of the spectrum where we have this problem where a bunch of the spectrum was missing, and it's always doing our frequency hopping. So let me go ahead and disable the digital channels. We don't need to look at that, and we also don't need to look at the bus. Let's get rid of that as well. Did I do it? I don't think I did it. There we go. There it is. Now you can see that it looks quite nice. We don't have that missing portion anymore, and it's updating and it's doing random frequency hopping, and it looks quite good. But it still has some problems. There are occasional tiny parts of the spectrum missing, but aside from that, we have these lines. Remember, this is vertical, this frequency, this is time. These lines are not very well defined. They're quite thick, meaning that there is a lot of frequency, center frequency noise there. And if I look over here, you can see the spectrum is really dirty. And because the spectrum has all these tones and phase noise on it, whenever it computes the center frequency, you have this room where it's moving up and down. That randomness is a problem. This should be much better defined and much thinner lines, meaning the center frequency has to be much more accurate as a function of time. So there is another problem. Now if you look over here very carefully, you can see that there's some activity on this. And this activity tells me that there is some pollution on the PLL controlling the voltage controlled oscillator that was the main LO generator component. So we can go ahead and look at that voltage that controls the VCO and see if that voltage is actually clean or not. Because if that voltage is not clean, we're going to have a mess on our hand over here, and that will tell us if the problem is coming from the PLL or is it from somewhere else. Just to remind you, we're talking about this component over here. We already addressed the wrong code that was being sent to the Silicon Labs synthesizer, but now it seems like we have some additional noise present due to this guy. Now this guy has some circuitry on this board over here which controls its center frequency. Let's go ahead and look at that signal and see if that signal is clean or not. And that's really easy to do. Now this is an analog signal, it's no longer a digital signal. So instead of using the digital inputs of the instrument, we're going to use one of its analog channels, and I have connected one of the probes to channel 3, and I'm going to use channel 3, and the reason I've chosen channel 3 is because the color looks nicer against this curve over here. So let me go ahead and connect that and see what it looks like. Alright, I went ahead and I connected the channel 3 to the tune voltage of the VCO, allowing us to see how clean that voltage is. I'm going to go ahead and enable channel 3, and there it is. And that looks really bad because this is on a 2 volt per division. So there's a lot of noise on the tune voltage of the VCO, and that's obviously not good. Now I noticed another unusual behavior from the instrument. This is probably one of my only other complaints about it. And the fact that the instrument has to choose the number of points and the sample rate of the ADC on the analog channels automatically, but I'm looking at the 1 millisecond duration of the RF versus time. So this should be 1 millisecond of time as well for the ADCs that are capturing the analog inputs. But because it's only doing 10,000 points and 1 million points per second, they don't seem to line up quite right, and the instrument has this running start where it shows this channel running for a while it's not updating the RF versus time trace, and this causes confusion, and I'm not sure if this is a bug or it's just that because the sample points don't match up. I wish they would make this a little bit more clear for the end user. Now, I've used this instrument a lot. It's one of my favorite instruments in the lab, so I'm really familiar with all of its eccentricities, I should say. But this is something that can easily fix, and then it would become a lot easier, and especially for very large, huge time scales looking at spectrum, this can be a little bit annoying. I can fix that a little bit by going under require menu, and instead of just selecting 10,000 points, I can choose to record 10 million points. And by choosing 10 million points, the instrument automatically has to increase the sampling rate to 1 gigasample per second, and that problem goes away. And let me press the RF here so that the RF trace comes in the front of that purple trace, channel 3. And now we can see that indeed we have a lot of noise, but looking at it at this scale is difficult because you can't tell if there is any correlation between the noise and the actual frequency uncertainty. But we can zoom in and see if that's the case. Let's do a single capture here. And then it should show up any moment. There it is. And we're going to zoom into it. Now this is what I was saying before. I wish there was a way to just reset this back to 0 so it's always in the middle of the screen. But check it out. The noise isn't always there. It kind of comes and goes. And it has periods in which it is completely quiet. So let's zoom in a little bit, see what happens there. And look at that. There are indeed some time where there is no noise. And this is an interesting thing because it means that there is some correlation between the tune voltage of the VCO and the SPI and the I2C activity. And when there is no clock activity, there is also no noise on the tune voltage of the VCO. So we can fix that, but I want to make sure that's the case. Now, right now, this spectrum is being computed in this duration of time. Now, unfortunately, this duration of time is longer than the duration of time where the spectrum is, where the noise is not present. And I want to look at the spectrum only in that duration to see if it's still noisy or not. And then it will confirm my suspicion that this is a problem. Well, I can't do it right now because the resolution bandwidth that I have selected for the spectrum analyzer is simply too low. And it means that the amount of data the instrument needs to physically collect in order to be able to do that resolution bandwidth simply doesn't fit within the time that this signal is quiet. But I can also change that. I can go under the resolution bandwidth and I can change the resolution bandwidth and make it larger. So let's go ahead and make it larger. Let's make it 500 kilohertz and do another single trigger. And you can see that now it's so much smaller even though the horizontal axis didn't change. Obviously we're going to lose spectral resolution. That's a consequence of not having the resolution bandwidth. But now I can move this around and see if the spectrum becomes quiet. And check it out. Let's go right here and check it out. It's clean. By moving it right in the quiet area, I can see the spectrum is clean. I want you to appreciate how valuable this information is. Again, I want to repeat that these measurements are very, very difficult to perform without this type of correlation. You would be scratching your head trying to figure out what it is that you're looking at. But I can look at exactly what is happening here. Spectrum is noisy, has harmonics, because this is very periodic. Here, the spectrum has a broadband noise on it because it's non-periodic. And in the middle, the spectrum is clean because there's no noise. This is quite amazing, and I can go ahead and fix that. And then you can also see it here, how this line is so well defined here, but it has noise on it here. Again, it's well defined, noisy, well defined, noisy. Well, that's the reason. It's because you have a nice clean signal here, but you don't have a nice clean signal here. So this is our second problem, the noisy LO carrier. I can go ahead and fix that as well. So let's go ahead and put this in the continuous scan again. And we can go ahead and try and see if I can fix the noise. Let me fiddle around here with my circuit and see if I can fix this problem. It looks like we've got some isolation issue here. And I'm going to try and correct this isolation by doing this. Let's see, does that clean our problem? Let's take a look here. Ah, there we go. Gone. Now we don't have any noise on channel 3 anymore. So let me go ahead, get out of the zoom menu, and look at how much nicer the frequency hopping is, and our signal is much better defined now. Let me go under my resolution bandwidth again and put it back to auto so we can get a nicer spectral view there. It's going to do the computation, and there it is. It looks pretty good. We got rid of all the unnecessary tones that were there. We now have a much better dynamic range. Our frequencies are so much better defined. You see how clean the frequencies are? They don't seem to have any problems anymore. So I'm quite happy with that. Now we can take the next step. So now that we are satisfied with our frequency hopping algorithms and our center frequency being nice and clean, we can look at a spectrogram. And there is an additional problem that you occasionally see here, and that will become clear in the next part of our test. But overall, it seems like we're doing the correct frequency hopping and everything looks good. So now we can go ahead and disable this. We don't have to take a look at this anymore. Turn this off. And let's go ahead and turn on our spectrogram and take a look at the spectrogram as a function of time. Now we should be able to see our various channels as hotspots appearing across this rolling spectrogram. Now, one of the features I wish this spectrum had was I wish I could choose how fast it gets updated, because as far as I can tell, I'm not able to actually do any edits on the spectrogram itself except to turn it on and off basically. So yeah, I can't quite figure out how to change it. Right now I put it on triggered mode, so now it triggers on the events that were defined in the trigger menu. But now if I wait long enough, I will see that individual channels slowly forming. You can see hotspots showing very distinct frequencies in which the signal hops in between. Now there is some horizontal traces that seem to be appearing as if the frequency is not very clear, and I'm not sure how well this shows up on camera. I'm sorry if it doesn't, but I can see hotspots here, 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 and so on and on. So you can see that the frequency hopping is indeed happening. Now, one of the other things that would be pretty interesting to take a look at is to see if we have the correct channel transitions and what happens between one channel transition to another. Because if you look occasionally, you see this long line that just appeared here. Why is that long line there? Why do we get this bleeding between the channels as the frequency is hopping? Well, for that, it would be interesting to take a look at one of the signals coming out directly from the Silicon Labs IC. Well, right now we don't need the spectrogram anymore. We can go ahead and turn that off. And we're back to looking at our spectrum by itself. And then this is where I want to take a look at the output of the Silicon Labs IC directly, and I have connected it to channel 3. So I can go ahead and enable channel 3 right over here. And there it is. We can see, in fact, the output coming directly from the Silicon Labs, and I can do a single capture. And one of the very first things to note is how nicely it actually does intensity grading on this signal. Because remember here, this signal is changing in frequency constantly. And as a result of that, where it's really bright is when the frequency is very high, because you have many transitions, and when it's dark, the frequency is low. So there's fewer transitions. So it's quite interesting to see this and see how nice they do intensity grading. Again, this is not a surprise. Tektronix has been doing this for a very long time. They know what they're doing on that. But here we've captured an interesting phenomenon. Here we can see that there are situations where the output of the Silicon Labs is actually stable for a short amount of time. So that's now has to do with the communication protocol between the microprocessor that's used and the Silicon Labs, and the timing may be wrong, or some other resource of the microprocessor may be occupied doing something else, and these delays are what causes the spectral leakage, and which is unpleasant. You don't want that, and it doesn't always show up. If I do a single capture again, you can see that it's not always there. So it has to do with the interrupts that are driven from the microprocessors. And another problem that you could catch using this correlated signal. But let me zoom in and show you something else quickly before we move on. Let's zoom in. Obviously, if I zoom in all the way, eventually I will see the signal. That's to be expected. But let's look at somewhere where we see maybe a couple of these. Maybe this one. Let's do a single capture here. There it is. And you can see that the spectrum looks nice here. And I can go ahead and do a search again and go left and be right there at the transition point. So I can zoom in a little bit, and you can see during the transition I will have two peaks, and this is the transition behavior from one channel in the middle of two channels and the other channel. And this is where you saw the lines right across that spectrogram. This answers the question of why that is. It's a byproduct of the way the signal is calculated, because you're looking at a windowed signal that changes frequency from one point to another. So it's not actually a problem, because the receiver would ignore those transition points and only sample the data at the center of the channel timing. So this kind of answers the question, and we've basically pretty much solved all of the problems of the system, so I'm quite happy with that. And obviously we can keep going and dig further, but for the purposes of showing you what the instrument can do for this test, I'm satisfied with that. So let's go ahead now and address the other point that was in the sheet at the beginning on the presentation, is that they wanted to figure out what the bandwidth of this detector is. And we can measure that, and it's quite difficult to measure this any other way. So let's go ahead and take this out of the unit and just try and figure out what its bandwidth is using some other instruments. And that should be pretty interesting as well. And in order to do this next measurement, I have disconnected the input of the amplifier. It's no longer being driven by our first mixer, but it's coming from another synthesizer. And I'm using, if I can get the camera pointed correctly, I'm using the Tektronix MDO4104C-6, which is a 6 GHz synthesizer capable of a whole bunch of different vector modulation. I've done a full teardown and review of this unit. I quite like it. It's nice and portable and it has quite a bit of options. I wish they had updated the firmware on this, because it's still running the same firmware from when I upgraded. I couldn't find a newer version of it. But I have set this guy to do ASK modulation. Now ASK is amplitude shift keying, and the reason this is beneficial in this case is because by choosing 2 ASK, which means just amplitude on and off, and by changing the rate of the ASK, I can measure the bandwidth of the amplifier, the detector, because the detector is measuring the input signal amplitude, and if I change the input signal amplitude rapidly, I can estimate what the maximum bandwidth of the detector is. So I'm taking the output of that using the 2 ASK modulation, and I'm putting it directly into our little amplifier here, and the output of that amplifier then goes into the MDO. And right now there is no modulation being applied, so we're only looking at a CW pulse on the MDO, and you can see the CW pulse quite clearly. It's a 3.6 GHz signal just like before, and I'm looking at the spectrum of it. Now I can go ahead and enable one of our RF traces. Oops, didn't want to do that. One of the RF traces versus time, and I'm going to click on amplitude. And obviously the amplitude of this signal as a function of time is constant, as to be expected, because it doesn't have any actual modulation on it yet. So I'm going to go ahead and enable the modulation using the Tektronix TSG, and if I enable the modulation, and there it is, we can clearly see that there is indeed modulation present, and this is a 100 microsecond per division. So you can see that, you know, just under every 100 microsecond we are changing the signal amplitude. And if I go ahead and go around using this the search, and you can see that over here we're going to have our signal tones present, and right outside of those regions we're going to have very, very little power present. You can see that the signal amplitude is very small. So this is what ASK is. No problem. I have also connected the detector output of the amplifier to channel 2 of the oscilloscope. Now we can go ahead and enable that, and check it out. Very nicely we can see the clear correlation between the output signal power and the detected value. Now this is an inverted relationship. The higher the output power, the lower the detector voltage is. So you can see that the square wave coming out of our detector output matches and correlates to the square wave, which represents the amplitude modulation as a function of time. Again, a very powerful tool that this MDO provides. We can go ahead and zoom in and take a little bit closer look here. And you can see that indeed there is a finite rise time to this signal, and it doesn't have an infinite rise time as to be expected, because the detector has a finite bandwidth. Now I can go ahead and increase the modulation rate. As I increase it, you can see that it becomes more and more clear that the bandwidth is limited. So let's go ahead all the way to 1 mega symbols per second and zoom in and check it out. Indeed, we have a significant time that it takes the detector for the output to recover, but as soon as signal is present, it jumps down very quickly. So it has this non-symmetric behavior where it takes a long time for it to relax back to its default position, but as soon as you apply power, it gets pulled down very quickly. This is normal for detectors. Most likely it's using a diode. So As a result of that, we can now estimate that, okay, at 1 megasymbols per second, this is 4 microseconds, so we have our time divisions here, it's about 2 time divisions. That's the best we can do. So from this, we can easily estimate the bandwidth. We can even put markers there, measure the rise time, measure the fall time. I mean, just like any oscilloscope, we can do all of this functionality without any problems. And this is again the powerful functions and the features of the MDO, being able to do this correlated measurement. This would be normally quite difficult to do if you wanted to see correlation between these. And more importantly, if there was a problem and there was an issue where, for example, the signal had some weird behavior, you could catch that correlation with the RF signal quite easily this way. So now that we are satisfied with this, the only other remaining part of our experiment is to simply connect the amplifier back to the mixer and turn on our IQ modulator and actually do our final experiment using the signal view and be able to do signal demodulation using this mixer as the first modulator. So let's go ahead and set that up, and then we can go back to the computer, launch signal view, and take a look at that. And here's the setup for the final experiment. I apologize for the handheld. There's a lot of stuff that I want to show at the same time. So here I'm setting my modulation. You've seen me do this before in a couple of other videos. So here I'm setting my IQ modulation. I'm doing a 32 QAM and a 16 QAM modulation. And we're taking the output of that, coming here into our setup, going into our mixer, and of course then the output of the mixer, after all the problems that we had here have been corrected, goes into the unit itself. And you can see currently I'm actually measuring the spectrum, but here I cannot do digital demodulation directly, but the signal view that it runs on the computer and it connects with a USB to this or Ethernet or whatever you want, then you can do signal demodulation on the computer. And finally, after having corrected all these issues, we can go ahead and see how good the constellation is on the computer. So let's go ahead and take a look at the signal view software. I've shown this before in the original review of the MDO4000B, but here we're going to take a look at it again to get the performance of our link after it's been corrected. So let's go ahead and add some windows that we like to analyze. So this software has been updated since the last time I used it, and it has a whole bunch of other features, including the tracking generator and return loss, which is for the USB based spectrum analyzers that Tektronix has made recently, and I'm going to do a full review on that separately. For now, we're going to look at only the type of signals that we're interested in for the purposes of this experiment. So let's take a look at the spectrogram anyway. And under the digital modulation, because we know we're doing digital modulation on it, you want to see the constellation. Let's look at the eye diagram. Signal quality is nice to also take a look at. It's also important to note that there's a whole bunch of RF measurements. I've shown some of that before. There is analog modulation, as well as all the typical ISM band protocols, which are very popular obviously for product development, such as Bluetooth, wireless LAN, 802.11ad, and so on. And all those are part of this. They're not all free, of course. You have to purchase them separately, but this type of analysis at the cost that they're being offered is actually quite attractive. So let's go ahead and click OK. And now we're going to get all our different windows. My computer is quite slow here, the one that I'm using in the lab, but all the windows will now pop up, and we can go ahead and configure them as we want, and we can reconfigure the windows and move them around and change the dimension and so on. So in fact, let me see if I can go ahead and change. You know what? I'm going to tile them a little bit differently. Let's see what happens if I do like this. There you go. This is a little bit bigger. That's what I wanted. So let's go under the spectrum here. Let's set our carrier frequency to what we know it should be, which is 3.66 gigahertz. I have already turned off the frequency hopping because this software cannot track our custom frequency hopping anyway. So right now is at a standard frequency fixed, it's not hopping anymore. And there's our spectrum, and you saw this spectrum originally when I was looking at it on the unit itself. And under the modulation, we can go ahead and enter our modulation information. I know I'm using 32 QAM, and the baud rate here is 10 million symbols per second, but the filter parameter is 0.35. 0.35, and it's the same as the root raised cosine as it is indicated here. We don't want any equalization. I'm not going to turn that on. And let's change the analysis time to look at 256 symbols at a time. And let's go ahead and turn off the traces so we can only look at the points. And check it out. Here it is. You can see clearly our 32 QAM constellation. You can see that it doesn't have a lot of phase noise. It doesn't have a lot of SNR limitation, but it is skewed in one direction. And that has to do with the linearity limitation of the modulator that I'm using. But nonetheless, it looks pretty nice, and it's reasonable in terms of its SNR, but like I said, because of the linearity limitation, we now see this effect and then we can go ahead and address it and figure out, okay, this problem we're seeing in the mixer now has to be addressed, otherwise we're not going to have a very good link quality. In fact, you can see over here the signal quality is reported. The EVM is 13%, minus 17.5 dB, which is not very good, and this is another way of figuring out this problem exists and going to correct it. Another advantage of having the software work with the instrument. And they've continuously updated the signal view, and it has better capabilities, and some of the bugs that I was finding before have been resolved, and you can see that the spectrogram continues to build. So I'm quite happy with it, and I'm excited to use it with some of the other USB instruments in the future, and I will show you some more of the detailed operation of this software. But this would then conclude the experiment because we've fixed all the problems, and now we have a constellation. This would have been absolutely impossible to capture with all the problems we had earlier on, and only after fixing it are we able to do this experiment. And there you have it, a close look at the MDO4000 series, including the teardown of the unit, which I didn't do on my review of the B version of it. And I hope that you enjoyed this. As you can imagine, there is a tremendous amount of detail in this unit which I still haven't covered. We didn't really look at the digital multimeter, the arbitrary function generator, its fast acquisition mode capabilities, and a whole bunch of software options that are built into it. But there's just so much to cover, it's impossible to show you everything, but I wanted to show you some of its main and clear advantages over traditional equipment with a different set of experiments, so you can get an idea of how well this unit actually works in different scenarios. My complaint about it still remains the same. I hope that they would make the unit faster, be able to build one that can handle a large amount of data. A couple of bugs here and there, I'm sure they'll be fixed in future firmwares. Overall, like I said, it's definitely one of my favorite instruments in the lab. And as you can imagine, the amount of effort that goes into making a review like this is just mind-boggling, because I have to design the experiments, I have to put it together, I have to test it in advance, I have to build all these faults into it, and every time that I review it, it's a different experiment. I typically don't tend to repeat my experiments, so that you can learn from the setup just as much as from the review of the equipment itself. And if you're interested in helping me out, I do have a Patreon account, you can help that, but you can also contact Tektronix or any other manufacturer that I review for. If you happen to purchase the equipment because of my review, you can let them know, and this will allow me to have a good relationship with them and continue to bring you some of the state-of-the-art equipment that they release, and this will allow us to do more and more interesting and fancy experiments here in the lab. And if you like the video, leave me a comment, let me know. If you have any suggestions, of course, I'm always open to hearing from it. And I've been posting a lot more to my Twitter account, so please check that out. And if you have any questions, I'll try to answer it. But I hope you enjoyed the video. I'm sure I'll make another one pretty soon.